The human heart is an autonomous engine of muscle, contracting roughly 100,000 times every single day. This single organ functions as two coordinated pumps, working in parallel. The right side drives deoxygenated blood through the pulmonary circuit to the lungs, while the left side forces oxygen-rich blood through the systemic circuit to the rest of the body. Understanding this mechanism requires unifying its anatomical structure, its electrical pacing, and its fluid dynamics. They form a single electromechanical continuum. Historically, clinical medicine measured the electrical signature of the heart blindly, relying on paper tracings to record the timing of events without a direct view of the mechanical deformation occurring inside the chest. Anatomists mapped the physical chambers and valves with precision, but these diagrams depict a static system, lacking the electrical overlay that animates the tissue and drives the blood. To understand the heart's pumping action, we must fuse the electrical spark, the structural anatomy, and the fluid dynamics into one unified, four-dimensional model. We begin with a structural cross-section of the heart, aligned to a clinical timeline. By tracking a single heartbeat, we can map the exact relationship between cellular electricity and physical fluid motion. The cardiac cycle initiates at the sinoatrial node in the upper right atrium. The specialized cells here exhibit automaticity, undergoing spontaneous depolarization to fire an electrical impulse that sweeps across the atria. On an electrocardiogram, this wave of electrical excitation registers as the P wave. Milliseconds after the electricity passes, the mechanical response follows. The atrial walls contract, reducing the volume of the upper chambers. This contraction forces blood downward. Oxygenated blood moves into the left ventricle, while deoxygenated blood fills the right. This event, the atrial kick, contributes the final 10 to 30% of ventricular filling. It stretches the lower chambers to their maximum capacity, achieving end-diastolic volume. The P wave is more than a signal. It's the electrical mandate for mechanical priming, ensuring ventricles are fully loaded before the main contraction begins. As the electrical wave hits the base of the atria, it converges on the atrioventricular node. Here, the rate of signal propagation drastically slows. This delay is a product of cellular geometry. The cells in the compact node have extremely small diameters, increasing internal resistance and slowing the flow of current. Low conductance gap junctions act as strict bottlenecks, further throttling the signal's transmission between cells. Conduction velocity through this node drops to roughly 0.02 meters per second. This produces a crucial delay of 120 to 200 milliseconds, represented on the ECG by the flat, isoelectric PR segment. Without this pause, the atria and ventricles would contract simultaneously. The chambers would fight for the same blood volume, collapsing the heart's overall pumping efficiency. The AV node's architecture enforces strict temporal separation of contraction, allowing fluid to fully clear the top chambers before the bottom chambers fire. Once the signal clears the AV node, it enters the bundle of His and shoots down the interventricular septum, splitting into the left and right bundle branches. The signal then enters the Purkinje fiber network, where conduction speeds reach 4 meters per second. This ensures the entire ventricular myocardium is activated nearly in unison. This rapid, massive depolarization wave creates the sharp QRS complex on the clinical timeline. The response is immediate. The thick ventricular walls tense and begin to forcefully ring inward from the apex toward the base. Rising pressure slams the mitral and tricuspid valves shut, preventing backflow and creating the first heart sound, or S1. During this moment of isovolumetric contraction, all 4 valves are closed. The blood volume is trapped and constant, while the internal pressure skyrockets. The QRS complex marks the exact millisecond the heart transitions from a passive filling basin into a sealed, high-pressure hydraulic pump. When the rising ventricular pressure finally exceeds the pressure in the aorta and pulmonary artery, the semilunar valves violently burst open. The cells maintain an electrical plateau, sustaining the contraction while the timeline draws the flat ST segment. This is the rapid ejection phase. Oxygenated blood shoots into the aorta for systemic delivery, while deoxygenated blood is driven into the pulmonary trunk toward the lungs. To reset, A wave of electrical repolarization sweeps the ventricles, recorded as the T wave. As the cells repolarize, the ventricular walls relax and pressure falls rapidly. The higher arterial pressure slams the semilunar valve shut, creating the second heart sound, S2. The T wave provides the electrogenic reset, allowing the mechanical pump to return to a state of diastole and begin passive filling for the next cycle. This chart shows the Wiggers diagram, plotting the electrical ECG alongside ventricular pressure and volume, scrubbing in perfect synchronization. Here, the P wave is the electrical mandate for final filling, resulting in the atrial contraction that maximizes ventricular volume. The PR segment is the physical pause required for fluid clearance, syncing with the precise moment of maximum end diastolic volume. The QRS complex is the trigger for pressure generation, aligning with the closure of the valves and the rapid vertical spike in ventricular pressure. And the T wave marks mechanical relaxation, where the fall in pressure allows the AV valves to open for the next filling phase. The heart orchestrates this dual-circuit pump against immense shifting pressure gradients, maintaining this sequence across billions of cycles. The system operates through structural diversity, deploying specialized slow and fast-conducting tissues to translate microscopic ion fluxes into the macroscopic fluid dynamics of life.